All right, welcome back. In class, we were working through this problem. Started looking at the area beneath the curve, and the idea was to estimate the area by overestimating with rectangles and underestimating. And we're going to do this for various number of subdivisions. So the first one is one subdivision. So of course, the overestimate would be to take the largest value across the whole interval and say, okay, well, let's make that the height for the whole rectangle. And that would give us an area of 64. So we know our area, which is the area beneath the curve, is definitely less than 64. And then as far as the underestimate, we pick a value that's below everything on the interval, and that would give us a height of 0. So we know we have more than 0 area. But we kind of already knew that. So not a lot just from one rectangle. So we do the same thing now, except we're going to do 2 rectangles. Now there's nothing that says that our subintervals have to be the same size, but we generally do that to make the math easier. So that means for my upper estimate, I'm going to cut the interval from 0 to 4 into 2 intervals. I'm going to cut it at 2, and so at 2 for my overestimate, I'm going to take the height that is the biggest over that whole interval, right, and form that rectangle. There. So form the rectangle that goes there. And then I'm going to go the interval 2 to 4, and I'm going to do the same thing. I'm going to form the rectangle with the absolute highest value across that interval as well. Okay, so my overestimate would be S upper 2, or S2, and that would be a width of 2 times a height of 4, plus another width of 2 times the height of 16. Right, and so we work that out. 2 times 4 is 8, 2 times 16 is 32, 8 and 32 gives us an upper estimate of 40. Now this is a better estimate than our 64. There's a lot less extra area outside those rectangles than there was in the first case. So that's a better estimate. It's a better estimate. We know a lot more about how big our thing is. It's definitely now smaller than 40. And then we do the same thing with the lower estimate. So for the first interval, 0 to 2, I'll take the absolute smallest value, which basically, once again, gives me a rectangle with a height of 0. And then the same thing when we get to second interval, right? I take the smallest height across the interval from 2 to 4, which would be at 2 squared. And so now we compute our underestimate, S2. So that's going to be 2 times 0 plus 2 times 4. Gives me a lower estimate of 8. Now I know for sure that the area beneath my graph is bigger than 8. That's better than what I knew before when I was dealing with it just being bigger than 0. Right? Because we can see there's a lot of area that our rectangles are not getting. A lot of area our lower rectangles are missing. And then we're going to continue this process. We're going to continue this process. You're going to turn in n equals 4. Right, that's your turn-in problem, is to divide it up into 4 equal intervals. All right, so you're going to turn that in to me as a turn-in problem. N equals 4. Okay, will be your turn-in problem. Okay, so you're just going to divide this up into 4 intervals, so that would be at 1, at 2, at 3, at 4, and do the same process for the upper and under estimates. Now we're going to do one more example here, and that is we're going to look at n equals 8. We're going to look at n equals 8. So if you're not quite sure how this works, hopefully this last example will clear it up for you. We're going to do n equals 8. So that means we're going to take the interval from 0 to 4 and divide it up into 8 equal intervals. So that means the first interval, each interval will be a half of a unit long. So you take the distance of 4 divided by 8. And so we're going to be looking at this first rectangle here, then this second rectangle, and then this third rectangle, and we just keep going. Now you can see here that these rectangles are leaving a lot less out than some of our previous examples. We just keep going through and doing that. And also at 4.5, or sorry, 3.5, and then finishing off there at 4. So to make the math a little easier here on these underestimates, or this overestimate, so we don't have to write out a bunch of stuff, what I want you to realize is when we do the area of each rectangle, they're always getting multiplied by the base, which is 1/2 everywhere through. And then the height is just the function value, whatever the x value is, squared. So for s upper 8, we can write it out like this. 1/2, and then the first value is going to be a half squared. And then 1 squared be the next interval. And then 3/2 squared. And then 2 squared. And then 2.5 or 5/2 squared. And then 3 squared for the next interval. Plus 3.5 or 7/2 squared. And then finally plus 4 squared. Okay, and then we just want to simplify that. So I'm actually going to group this 2 ways. I'm going to take all my whole number ones, my 1, my 2, my 3, and my 4. I'm going to put all those together in front. So I still have my 1/2 out here. I'm going to have 1 plus 4 plus 9 plus 16. And then I'm going to do my fractions. 1/2 squared is 1/4. Plus 3/2 squared would be 9/4, plus 5/2 would be 25/4, plus 7/2 would be 49/4. Now, when you add all these up, we're going to have 1/2. 1 and 9 is 10, and 4 is 14, and 6 is 30. And what about these? Well, the good news is they all have a common denominator. So we just start adding them up. 1 and 9 is 10, and 25 is 35. And then we have 35 plus 49. 35 plus 49 will be 84. Turns out 84 is evenly divisible by 4. And so that all just turns out to be 21. Okay. So in the end, we get that our upper estimate is 51/2 or 25.5. So we know that the area beneath our curve must be less than 25.5. Okay. And then we do the same thing for the lower estimate. We go through and we do that. So the lower estimate, we would take the lowest height possible, which would be 0 to start off with, then at 1/2, then at 1, then at 1.5, then at 2, then at 3, 2.5, then at 3, and then finally the last one will be at 3.5's value. Okay, and we work those out. So S lower 8 is still going to be 1/2, and that's going to be times 0 squared plus 1/2 squared plus 1 squared plus 3/2 squared plus 2 squared plus 5/2 squared plus 3 squared plus 7/2 squared. Now, there's actually an easy way to do this, and that is to realize that the only difference between, so I'm not going to add these up like I did up above. I'm going to kind of use a little trick here. Realizing the only difference between this list of addition problems and this list is the 4 up here has been replaced by a 0 down here. So if I just remove the 4 from up here, that's 16. Those things totaled up to be 51/2. So this is going to be 16 smaller, and then times a half, so it's actually going to be 35/2. This is actually going to be 35/2, which is 17.5. So much better underestimate than what we had earlier. So overall now we can say this much, that the area beneath the curve is somewhere between 17.5 and 25.5. Now the idea that we're going to be building to here is that we're going to let the number of rectangles go to infinity. Right? We've talked about limits going to infinity, so we're going to set this up as something we can take a limit going to infinity to, so that we can actually get the actual area. And what we'll actually see in one of our examples is that both the underestimate and the upper estimate actually go to the same thing, which has to be the actual area. That's what we're going to be building to, but we have to get into some notations first. We're going to have to look at some examples to kind of build up to the tools. Build up the tools that we need to be able to do that. And that's what we're going to be coming up across in the upcoming videos.